But again, it may have been a while. So let's start off with the first thing. The first little section of chapter 3.1 talks about inverse functions. Now, before we get into inverse functions, we define what it means to have a one-to-one function. A one-to-one function is a function that for every element in the range corresponds to only one element in the domain. One element in the domain maps to one element in the range, 1 to 1, which means by definition, if f of a equals f of b, that will imply a has to be equal to b, because there's only one element in the domain that's going to map to the range. So if the ranges are equal, the domains have to be equal to each other. But the way we used to do it in, like I said, high school, was that when we were looking at a particular function, trying to figure out if it's one-to-one or not, we had a special type of test called the horizontal line test. Remind yourself, there were two different line tests that you guys studied in high school algebra 2 or whatever. There was the vertical line test, which tells you if you had a function or not. Vertical line goes up and down, and if it passes through graph only once, then the function it is a function. If it passes through a vertical line passes through a graph more than once, it was not a function. To make it the one-to-one function, you have to have a horizontal line test. Horizontal line test runs from side to side. And if you graph it, if a horizontal line intersects it more than once, it is not a one-to-one function. But if it only intersects it once, it is a one-to-one function. So let's take a look at this guy here. Let's take a look at graph of f of x equals x squared. You do not need a fancy handy-dandy calculator for this guy. What does the graph of f of x equals x squared plus 2 look like? X squared is a what? Plus 2 is going to do what for you? Up 2. 1, 2. Looks like that. Is this function one-to-one? Horizontal line intersects it at more than once. Remember the classic line test. If any kind of line intersects more than once, it fails. This guy is not 1-1, one-to-one. Does that make sense? Well, let's take a look at this guy. Now this guy, again, we can do it on our calculators, but this does have a vertical asymptote at 2. And if I graph this thing on my calculator, which I brought to class today, we get this, x divided by parentheses, x minus 2. And I'm going to hit the old zoom 6 on it, and I get this picture that does this. It's there, goes through the origin, drops down, comes up here, goes over here, and I do have that vertical asymptote right in the middle. Question, though, is this guy one-to-one, yes or no? Any horizontal line intersects it only once. So this guy the answer is yes to one-to-one. This guy is a one-to-one function. And how you basically tell is basically graph it and look for that horizontal line test. Now that being said, there's a reason why we're studying these special kind of one-to-one functions. Next definition is the definition of an inverse function. Now, the big idea behind inverse functions. So let me give you the big deal on this. Inverses. You got x, you got y coordinates of a function. X is your input or independent variable. Y is the dependent or output variable. So you have something like you have a circuit. So you want to put in amps and you want to crank out voltage. So you tell the little function the certain amps that you're going to have, and then your output would be how much voltage this thing's going to generate. Does that make sense? Input, output. But what if you would like to switch that up? I would like to input the voltage and the output be the amps. So I basically want to switch the roles of x and y, switch the roles of independent, dependent. Well, when you do that, that is called an inverse function. You're turning the x and y back on itself. You're switching the x and y, the independent and dependent variables. So, again, reviewing this as, like I said, as a classic review, let f of x be a function such as 1-to-1. First off, before you can even talk about inverse functions, the real deal is it has to be a 1-to-1 function first. That goes to the point a, b. Then f with a little minus 1 above the little f there, x, is called f inverse of x, is called f inverse of x. Rules we have. If I take the composition, remember composition, plugging the one function into the x of another function. If I take the composition of a function with its inverse and clean it up, I always get x out of it. Don't cancel each other out, and x will be the only thing left over. That's what happens with inverses. f inverse of x will go through the point BA. And remember, the original function went through AB. The inverse goes to the point BA. Okay? It switches the x and y. And since it switches the x and y, one other little notation you can expect on inverses is the domain of f of x is going to be the range of f inverse of x. And the domain of f inverse of x will be the range of f of x. The domains and range are going to switch with the inverses because the x and y is a switch. Finding inverse functions is this. There are basically 5 steps to finding an inverse function. Step number 1, you've got to make sure the function is 1-to-1. If it's not 1-to-1, it does not have an inverse function. Step number 2, replace the notation f of x, g of x, whatever you happen to have, with y, because that'll make the math easier. The most important step in terms of finding inverse functions is step number 3, which is interchange or switch the x and y coordinates. So wherever there's an x, put a y. Wherever there's a y, put an x. That makes inverses. And then solve for y, and then the last thing you're going to do, well, that's the big algebra step right there, and then replace y with f inverse of x. You've declared what the inverse function is going to be. So let's take a look at some examples based upon this B and C levels that I've created here. It says this: verify that the functions are inverses of one another. The key word is the word verify. Giving you guys helpful hints on the old web work type thing here. Verify the functions are inverses of one another. Well, the trick for checking for inverses is that composition statement right there. If I take the composition of the two guys and plug one function into the x of the other function and clean it up and only x pops out, they're inverses. If something other than x, 2x, x plus 1, whatever, then they're not inverses. Now, with this one, there's 2 ways you can officially verify. I can take this function right here and actually find the inverse of it and see if it's this function over here. But that's going to be the long way. The easiest way to do this is take the composition of the two. And remind you, f of g of x. Take the composition of these two. This is f of g of x, and who's on the outside? F. So f is your commander. So what does he look like? He looks like the cube root of, leave a little blank for x, plus 4. That is what f looks like. But it's f of g of x. So what's inside the parentheses, g of x, is going to replace the x in the original f function. There's my parentheses. There's where the x was at, and I'm plugging in the g function, which is x cubed minus 4. Now, clean this guy up. This would be the cube root of, well, since there's nothing really in front of that x cubed minus 4, you can drop the parentheses, x cubed minus 4 plus 4. Order of operations, what happens to the 4? I got a minus 4 plus 4. They cancel, leaving you with the cube root of x cubed. And what do cubes and cube roots do to each other? What's the way you're left with? X. And since I got x out of this thing, and the thing tells me, my little theorem up here, that with the composition of the function with its inverse, if I get x out of it, they're inverses of each other. So the question is, verify that the functions inverses each other. Well, therefore, g of x must be the same as f inverse of x, because I got x out of this thing when I cleaned it up. Does that make sense? They are inverses of one another. What's that? Every problem that says verify, because in the sense that verify, they're going to give you 2 functions. They're going to ask you, are these 2 inverses of one another? Yes or no? This is the fastest way of doing that.
But we can do it the other way.
You can do it the other way, but you're going to see that sometimes doing it the other way is going to be a little bit longer. Let me explain. Flip the page. Look at these directions here. Now, notice the difference in the directions. The directions on these guys are find the inverse for each of the following. I didn't say verify anything. I'm giving you one function. I'm telling you find its inverse. All right, so let's do this in steps. So this first guy, let me blow it up a little bit so you guys can see it. K of x is equal to x minus 1 cubed. The first thing you need to do is step 1. We've got to check this thing for one-to-one functions. How do I check for one-to-one? Graph it. X minus 1 cubed. Well, this is an x cubed graph, which is a squiggly line. Minus 1 is going to shift it which way? Which one? Left or right? Inside the parentheses works opposite. Go right 1 unit. So this is over here at 1. And this is what my graph looks like. You could also put him on the calculator if you would like to. And I will do that just to prove it to you guys. Parentheses x minus 1 cubed. But my point is, you don't have to use a calculator on each one of these problems. So, yep, there's my function there. Is it one-to-one is the big question, though. Yes, it is. Any horizontal line only intersects once. So, yes on the one-to-one, so we get to continue on. Step number 2. Replace k of x, or whatever the function is, with y. That gives me y is equal to x minus 1 cubed. Step number 3, and this is the most important step in terms of inverses, and that is switch the x and y coordinates. What is that going to give you? X equals y minus 1 cubed. Step number 4 is equally important. You got to solve for y. What's your first move to solve for y on this thing? I take the cube root of both sides. This would give me the cube root of x is equal to cube, and cube root cancel, leaves me with just y minus 1. Now I want to solve for y, so I'm going to add 1 to both sides. This is going to give me y is equal to the cube root of x minus 1. Plus 1. Got to add 1 to both sides. Y equals the cube root of x plus 1. And then you got step number 5. You found the inverse. Now you have to label it. Remember, in calculus, labeling is everything. This guy originally was called k of x. So what's this new inverse function going to be called? K inverse, the rule minus 1 means inverse of x, equals the cube root of x plus 1. And that is my solution. Does that make sense? Look at this next guy. Put a big star by this next guy, because you always see this one on the test and the final exam. Guaranteed. All right. Same directions here. Find the inverse of the following function. Well, the first thing I want to do is graph it. This thing's going to have a vertical asymptote over here at -1. I can tell you that, because -1 doesn't exist on the graph here. But here we go. I'm going to graph it. Parentheses 2x minus 3 divided by parentheses x plus 1. Zoom ticket. And this is my graph. You've seen something very similar to this just a few seconds ago. I got this graph that comes in here, does this, and then comes down here and does that. The question is it one-to-one? Yes or no? Any horizontal line only intersects one spot. So yes, once again on one-to-one. So we continue on. This guy has an inverse function. Step number 2, replace the function, in this case g of x, with y. Y equals 2x minus 3 divided by x plus 1. And the next thing you get to do is most important step. Step number 3 is actually the inverse step. What am I going to do? Switch the x and y coordinates. This is going to give me x is equal to 2y minus 3 over y plus 1. The reason why they love to put this problem on the test and the final exam is because of the algebra you have to do. Your mission now is solve for y. How are you going to solve this thing for y? Multiply on both sides, get rid of fractions by y plus 1. This is going to give you x times y plus 1 is equal to 2y minus 3, because the y plus 1s would have canceled here. What's your next move? You're trying to solve for y, so you don't want any parentheses on this thing. So you want to distribute after you get rid of your fractions. So I'm going to distribute, gives me xy plus x equals 2y minus 3. Just like we had when we did dy dx, solving for implicit differentiation, I had to solve for dy dx on that stuff. In this problem, I got to solve for y. How do you solve for a variable? Get all the variables with the variable that you want on one side and all the other guys on the other side. So I'm trying to solve for y, so keep your eye on the ball here. So I'm going to subtract 2y from both sides, get my y's together. At the same time, I'm going to subtract x from both sides. This will cancel, this will cancel. This will leave me with xy minus 2y is equal to, this would have canceled, this cancels, negative x minus 3. And here's probably the most important step of learning, and same idea from that differentials, solving for dy dx on implicit differentiation stuff. How am I going to solve this thing for y? What am I going to do now? Pull the y out, factor the y out. That gives me y times x minus 2 is equal to negative x minus 3. And then the last move, divide by x minus 2 on both sides, get that y by himself. Leaves me with y is equal to negative x minus 3 divided by x minus 2. Am I done? No, we only stopped at step number 4. What is your step number 5, the final glory of getting the inverse answer? You've got to figure out what the function was called. It was called g in this problem. So now we replace y with the inverse notation. G inverse of x is equal to negative x minus 3 over x minus 2. And there is my solution. Does that make sense? Let's take a look at the next one. The next one's down here is h of x equals x squared plus 3. Directions say find the inverse function, if possible. Well, first thing you should do is check for 1-to-1. Well, this guy, I think we can graph it without a calculator here. X squared plus 3. What is that? Parabola shifted up 3 units. 1, 2, 3. It's a parabola. Question still stands. Is it 1-to-1? No. Horizontal line intersects more than once. Intersects twice. So this is not 1-to-1. So what is my answer to this problem? No inverse function. None, does not exist, whatever you want to put. I'm just trying to be fancy about this. Now, understand, there's a huge difference between inverse function and inverse relation. An inverse relation, you just switch the x and y. And that's just going to give you an inverse relation. Just switch the x and y. You can do that with any kind of problem. But with this one, we're looking for inverse functions. And the definition says you've got to be a 1-to-1 function first before you have a chance of being an inverse function. So if you fail 1-to-1, you won't be an inverse function. All right? Again, I'm approaching this as a review. You should have seen all this stuff before. Granted, it may have been many years ago. The next one is this, the graphs of inverse functions, and how you can figure out what the graph is. You can look at pictures and tell whether they're inverses of one another or not. And the theorem is this. Let the graph of f inverse of x be constructed by, the graph of f inverse of x can be constructed by mirroring the graph of f of x over the line y equals x. Okay? So, you see this graph right here? F of x equals the square root of x. Let's graph that guy, square root of x. What does that graph look like? Well, I'm going to start plotting points. I can't plot negatives because you can't take the square root of a negative number. But I can plot 0. What's the square root of 0? 0. Square root of 1 is 1. Square root of 4 is 2. It starts at origin and kind of bows out. That is the classic y equals the square root of x graph. You with me? Now, what this theorem says is I can look at this picture right here of the original function and I can see by the mirror image bit of what the graph of the inverse function is going to look like. Well, first thing you got to have is you want to draw the line y equals x. Y equals x is a line that splits the splits the first and third quadrants right down the middle. Y equals x. So it goes right through here. This is the line. Y is equal to x. Slope of 1. Okay? Splits it right down the middle. Now what you're going to do is take these points and do the inverse. Remember, inverses switch the x and y coordinate. But this point was 0, 0. So the inverse is going to be 0, 0. This point is 1, 1. So the inverse is 1, 1. But this point is 4, 2. So what would the inverse point be? 2, 4. So 2, 4 would be right there. And now connect your dots. Connect these two, connect it to this one, and keep on going. And if you notice, they are mirror images. If you turn it this way, you can see they are mirror images about this line y equals x going right down the middle of it. Does that make sense? So this is actually the graph of f inverse of x. Questions? This idea of looking at pictures and be able to tell what the deal is. All right, and again, one of the most important things about inverses is the second problem here. The following are points of the function. F of x has the points 2, 10, negative 1, negative 3, 0, negative 2, 1, negative 1, 3, 6. Find at least 5 points on the graph of f inverse of x. Well, what does an inverse do? Switches the x and y coordinates. So what are my answers going to be? 10, 2, negative 3, negative 1, negative 2, 0, negative 1, 1, and 6, 3. Notice what I did. I just switched x and y coordinates. That's the whole idea behind inverses. Does that make sense? All right. Now on this one, again, hitting one major idea behind all this stuff. Again, it's just defined to remind you of things that you may have forgotten many, many years ago. All right. I'm going to put a dot right here. I'm going to put a dot right here. All right. Remember, the domain of f of x is the range of f inverse of x, and the domain of f inverse of x is the range of f of x. An example. A function f of x is the following graph. Find the domain and range of the inverse function. Well, first, before I do that, let's find the domain and range of f of x. What is the domain of f of x going to be? No, they got dots here. So let's pay attention to the graph here. What is the definition of domain? X values. Well, where does it start at? Negative 2, and I put a dot there so we actually hit negative 2. And where does it end at? Right there. What number is that? 1, 2, 3, 4, 5, but it's right down the middle. So what is that? 4.5. So bracket negative 2, comma 4.5, close bracket. That is my domain of my function. I'm looking at the x-axis for domain. What is the range of f of x? Range is the only time I ever look at the y-coordinates of a graph when I'm answering questions about a graph. Y-coordinates. What's the lowest y-coordinate? Negative 1, negative 2. What is it? Negative 3, but I actually hit negative 3, so put a bracket on it. All the way up to this point here, the y-coordinate is 1, 2, 3, 4. What is it? 5. That is my domain and range. Therefore, f inverse of x. Here's the question. What is the domain of f inverse of x? And what is the range of f inverse of x? Well, I just switch them around because you switch the x and y coordinates. For inverses, you're going to switch the domain and range. So the domain of f inverse of x is the range of f of x, which is bracket negative 3, 5. And the range of f inverse of x is the domain of f of x, which is bracket negative 2, comma 4.5. There's my answer. Making the idea of switching the x and y coordinates, it also switches the domain range. Okay?